Welcome, curious minds, to another deep dive. Today, we're pulling back the curtain on something absolutely foundational to our modern world, yet often unseen: manufacturing systems.
Mhm.
Now, when you hear manufacturing, your mind might jump straight to, a giant factory floor churning out products.
Sure, the classic image.
Exactly. But what we're really talking about here is, well, a far more intricate ecosystem. It's where people, machines, and processes work together as a cohesive whole.
Right.
It's driven by fundamental ideas and principles, and crucially, it's always guided by what you, the customer, need and want.
And this deep dive is incredibly important for you, our listener, because modern manufacturing isn't just about making things anymore. It's a fiercely competitive arena.
Absolutely.
We're in a liberalized economy now, and that means, well, we're facing global competition right on our own soil.
Right here at home.
Exactly. Foreign capital, often bringing with it highly advanced manufacturing systems, is forcing companies to completely rethink their strategies. They have to innovate across critical dimensions: cost, quality, flexibility, and the speed of delivery.
All of them.
All of them. It's a fundamental shift, really. It demands more of a process orientation rather than the old fragmented functional viewpoints because, no part of an organization can truly work in isolation anymore.
It's a perfect framing. So our mission today is to truly unpack the fascinating evolution of these manufacturing systems.
Let's do it.
We'll explore the cutting-edge technologies that power them and, perhaps most importantly, how they integrate to create these incredibly responsive competitive entities.
Yeah, that integration piece is key.
We're going to uncover some hopefully surprising connections that will help you feel truly well-informed without getting bogged down in, endless technical jargon.
We'll try to keep the acronyms under control.
We'll do our best.
Yeah.
So let's start at the very beginning. When we say manufacturing system, what are those core elements? We mentioned man, machine, processes, guided by ideas, principles. What does that really mean on the ground?
Well, at its most basic, it really is that dynamic interplay you mentioned.
Yeah.
The people, the equipment they use, and the defined steps they follow.
Okay.
But the central driving force, especially in modern systems, is what we call the voice of the customer.
Yeah.
Customer needs aren't just something you consider at the end. They're woven through the entire manufacturing process, constantly refined by feedback loops.
So it's iterative.
Exactly. This whole system is designed to transform raw materials into finished goods through a series of value-added stages. The fundamental functions are always there, product and process design, planning and control, and the actual manufacturing itself.
The core bits.
The core bits. But the modern goal is intensely focused on integrating these functions, really trying to create a highly sensitive system that can respond quickly to those ever-changing customer needs.
That responsiveness seems absolutely critical today. And I imagine different competitive priorities really shape how these systems are built. What stands out to you when you look at different, say, global approaches?
Oh, they absolutely do. What's fascinating here is the stark contrast in priorities we've seen. If you look at Japanese firms, for instance, since the mid-'80s, their top priority has actually shifted to low price.
Low price.
Yeah. Quality for them has become almost a baseline expectation. It's just a qualifier now. You have to have it.
Wow, okay.
Their next priorities are things like rapid design changes and consistent quality. Now compare that to, say, Indian companies whose historical focus was largely on mass production, often within a protected economy.
Like different context.
Totally different context. But today, with global competition right there, the imperative is clear. They must adopt the right kind of advanced manufacturing systems just to stay competitive. It's really become a matter of survival.
That really highlights the pressure businesses are under. So, with that competitive landscape in mind, how have companies actually used technology to adapt, to fundamentally change how they make things?
Well, historically, manufacturing tech has progressed by, gradually replacing human power with machine power. We can broadly classify this evolution into, let's say, manual, mechanized, and automated stages.
Okay.
Automation, specifically, is where we apply mechanical, electrical, and computer-based systems to drive and control production. And the benefits are pretty profound. It improves product quality, ensures faster production and delivery, offers product flexibility, and significantly lowers labor costs in many cases.
Makes sense.
Within automation itself, we generally see three key types. There's fixed automation, which is ideal for high-volume, standardized products. Think assembly lines.
Right, unchanging.
Then there's programmable automation, which gives you flexibility for a variety of products, even if they're in smaller batches. You can reprogram the machines.
More variety.
Exactly. And finally, there's flexible automation, which tries to combine the best of both.
So if we look at those different levels of automation, how can we categorize these technologies more broadly? Maybe by their application areas, just to help us get a handle on this landscape.
Yeah, that's a great way to think about it. Shawnee and his colleagues offered a really useful classification by application. First, you have what they called engineering technologies.
Okay.
These are all about design and planning. Things like CAD, computer-aided design, CAE, computer-aided engineering, CAPP, computer-aided process planning, and CAM, computer-aided manufacturing. Basically the digital side of creation.
Got it. Design and planning.
Then there are manufacturing techniques. These focus more on the physical production. So robots, group technology, cellular manufacturing, FMS, flexible manufacturing systems, and ASRS, automated storage and retrieval systems.
The hardware side.
Pretty much, yeah. And finally, business techniques. These deal with the overall planning and management systems. Things like MRP2, manufacturing resource planning, JIT, just-in-time, Kanban systems, and TQM, total quality management.
Okay, so engineering, manufacturing, and business techniques, that helps. We've covered a lot of acronyms there already.
Yes, comes with the territory.
It does. But you said the real power comes from how they connect.
Yeah.
How do companies even begin to integrate all these complex pieces? Is there like a clear path or progression?
You've absolutely hit on the critical point. Integration. It's everything. Meredith and Hill actually classified advanced manufacturing technologies precisely based on their level of integration. It's quite neat.
Oh, interesting. How does that work?
So at level 1, you have standalone equipment. Think individual robots or maybe NC machine tools operating on their own.
Okay, isolated.
Right. Then comes level 2, which consists of cells. These are groups of equipment working together for part production, often using things like group technology and CAM. A highly integrated cell might even form a basic flexible manufacturing system, an FMS.
So grouped machines.
Exactly.
Yeah.
Level 3 involves linked islands. This is where you connect those level 2 cells into larger production systems. They're typically linked using systems like CAD-CAM, ASRS for storage, JIT principles, and maybe MRP2 for planning.
Connecting the groups.
Yep. And then at the top, level 4, you have full integration. This links the entire manufacturing function and all its interfaces through an extensive information network. This is what we commonly call computer integrated manufacturing, or CIM.
CIM. Okay, that sounds like the ultimate goal. Let's really dive into that idea of full integration, starting with CIM. When we talk about integrated in CIM, what does that really look like on the factory floor? What are the biggest challenges companies face trying to, stitch all these systems together?
Well, CIM systems are essentially about creating a unified nervous system for the entire factory. It's about ensuring an integrated approach to production processes, mainly through really efficient information handling.
Information flow.
Exactly. Leading to overall improvements in product quality and productivity. The real benefit isn't just, say, faster production in one area. It's moving from those isolated pockets of automation, those islands we mentioned, to a truly synergistic enterprise.
So integrated means?
It means connecting data, information, functions, processes, machines, devices, everything horizontally or vertically across the organization. So, for example, design talks directly to manufacturing. Production feedback instantly informs planning. Material handling systems coordinate with production control.
Everything talking to everything else.
Yeah, ideally, yes. CIM aims to weave together most of what we call hard technologies, the physical machines, and incorporates those systems management concepts like JIT, TQM, and MRP. The biggest challenge, honestly, it's often not just the technology itself, but the organizational shift required. Breaking down those traditional departmental silos is hard work.
I can imagine. So CIM is the big picture. Let's zoom in on some of those key components that make it all possible, starting right at the beginning of any product design. What is CAD, computer-aided design, and how does it, revolutionize how we create products?
CAD essentially involves specialized software and hardware that let engineers design products directly on computer terminals.
Right, on the screen.
On the screen. They can then analyze those designs using tools like CAE, computer-aided engineering, and store everything in electronic databases. It uses computer graphics to create geometric specifications. Some CAD packages can even generate the instructions for numerically controlled machines directly from the design.
Wow.
The benefits are enormous. You get faster design synthesis, analysis, documentation, which all leads to shorter product development times and lower design costs.
Speed and cost.
And accuracy. Plus, improved quality through CAE analysis and better communication because everyone's working from the same digital model. It really becomes the foundation for a manufacturing database, holding material specs, bills of materials, everything.
And you mentioned things like design for manufacturability.
Yes, that's a huge part of modern CAD/CAM. These design for X methodologies bring downstream concerns like how easy is it to actually make this thing or assemble it or service it right into the initial design phase? It avoids problems later on.
Thinking ahead. Makes sense. And how does group technology GT complement this design process and the manufacturing that follows?
GT is a really clever way to organize production based on similarity. It involves grouping parts that are similar into families,
Similar how?
either based on shared design features they look alike or common manufacturing requirements they need similar processing steps. This usually uses coding schemes, often numeric or alphanumeric, which makes it computer compatible for easy classification and retrieval. So you can easily find existing designs if a new part is similar, or pull up an existing process plan that just needs a few tweaks.
Saves reinventing the wheel.
Exactly. And GT is also key for forming what we call manufacturing cells. Groups of machines physically located together, dedicated to producing a specific family of parts. It streamlines the flow dramatically.
Okay, so we've designed it digitally with CAD. We've maybe organized parts with GT.
Yeah.
Now from design to actual production floor, what does CAM, computer-aided manufacturing, achieve?
CAM is really where the digital design meets physical reality. It essentially translates that CAD information into instructions for automated production machines.
The instruction.
Right. At its core, it involves using computer technology in the planning, monitoring, and control of the manufacturing processes themselves. This includes computer-run machine tools. You hear terms like NC, numerically controlled, CNC, computer numerically controlled, DNC, direct numerically controlled. But it also encompasses things like flexible manufacturing systems and automated assembly lines. It's the bridge from design to making.
And what about the physical side of advanced automation robotics? What kind of tasks are they best suited for? They seem to be everywhere now.
They really are. Think of a robot as a highly versatile, programmable arm, a multifunctional manipulator, as the source material calls it.
Okay.
It can be fitted with different end effectors, which are basically its hands or tools like a gripper to pick things up, or a welding torch, or a paint sprayer.
Got it.
And modern robots often possess vision capabilities now, making them incredibly adaptable. They're invaluable because they can work in hostile environments like heat, fumes, repetitive strain. They can work long hours with incredible consistency and output and perform tasks without fatigue.
Consistency is key there.
Absolutely. Their applications are incredibly broad. Material handling, loading and unloading machines, welding, painting, assembly, inspection, lots of areas.
So we've designed it. We're making it with CAM and maybe robots. But how are the actual steps to making a product determined effectively and consistently? How do you figure out the sequence?
That's where CAPP comes in, computer-aided process planning.
CAPP.
Okay. CAPP's job is to determine the precise sequence of individual manufacturing operations needed to produce a given part or product. These steps are typically documented on what's called a route sheet.
The recipe, basically.
Pretty much, yeah, the recipe for making the part. There are two main types of CAPP systems. First, there are retrieval-type CAPP systems, sometimes called variant systems. These use group technology, like we discussed, to categorize parts into families. Then they retrieve a standard process plan for that family and allow a planner to customize it for the specific part.
So start with a template.
Right. And then there are generative CAP systems. These are much more advanced. They use expert systems and AI techniques to create a process plan from scratch based on the part geometry and requirements without needing human assistance or relying on predefined plans.
Automatically generated plans.
Yeah.
Impressive. Beyond those individual processes for a single part, how were the large-scale operations planned and controlled across an entire factory? We're talking about really complex logistical puzzles here, right?
Exactly. That's the domain of manufacturing planning and control systems, often called MPNCS.
MPNCS.
These are sophisticated, computer-based information systems designed specifically to plan and schedule operations across the facility. They can do things like compare different production alternatives, monitor operations in real time, continuously update data based on what's actually happening on the floor, and project operating results.
A control tower for the factory.
That's a good analogy. They also encompass functions like order entry processing, shop floor control tracking jobs as they move through purchasing, and cost accounting. Often, these systems are closely linked with automated material handling, too. Think ASRS automated storage and retrieval systems.
Like robotic warehouses.
Essentially, yes.
Yeah.
Computer-controlled warehouses.
Cool.
And AGVS automatic guided vehicle systems, those little robotic carts you see moving parts around factories.
Right, the AGVs, okay. So when you bring all of this together, the CAD, CAM, CAPP robots, AGVs, the planning systems, what does it mean for how a modern factory can produce a wide variety of goods efficiently? This seems to lead us to flexible manufacturing systems, or FMS.
It does, and FMS really embodies that concept of combining flexibility with efficiency. It consists of clusters of automated machines, could be CNC machines, robots, inspection stations, all controlled by computers. The brilliance of FMS is its ability to produce a variety of products on the same machinery. The system can automatically change machine settings, tool paths, everything, based on computer instructions for the specific part coming through. Robots and automated material handling systems are integral for moving parts between stations.
So it adapts on the fly.
Pretty much. The basic components are usually automated processing stations, like those programmable machine tools, an automated material handling system, like conveyors or AGVs, and a sophisticated computer control system coordinating everything.
And people.
And crucially, yes, the human operator. They're still essential for tasks like loading raw materials, unloading finished parts, changing tools, maintenance, programming, troubleshooting.
All right, not fully lights out.
Not usually, no. The payoff for this complexity is huge, though. FMS significantly reduces lead times, cuts down on work-in-progress inventory dramatically, and achieves much higher machine utilization because the machines aren't sitting idle waiting for setup changes.
Can you give an example?
Yeah, the source mentioned a great one, General Electric's electric meters plant in New Hampshire. Apparently, it produces something like 2,000 different types of meters, all on the same flexible equipment.
2,000. Wow, that's incredible flexibility.
It really shows the power of FMS.
Okay, that's an incredible level of adaptability. Now let's shift gears slightly to some of the foundational philosophies that have shaped modern manufacturing, starting with just-in-time, or JIT. We hear about zero inventories. What does that truly mean in practice? Is it even possible?
JIT is really more than just a technique. It's a whole philosophy of manufacturing. Its core focus is intensely on eliminating waste and delays at every single stage of the process.
Waste and delays.
Yes. And waste, in the JIT context, is defined very broadly as anything other than that which adds value to the product.
Anything non-value added.
Exactly. Toyota, the pioneers of JIT, famously identified 7 types of waste things like overproduction, making stuff before it's needed, waiting time, unnecessary transportation, inefficient processing, excess motion, holding inventory, and of course, product defects.
Okay. The driving force behind JIT is what they call an unattainable ideal. 0 defects, 0 inventory, 0 lead time, and a theoretical lot size of just 1 unit.
Unattainable, you said?
Well, yes, achieving absolute 0 in all those is practically impossible. But striving for that ideal drives a continuous cycle of never-ending improvements. The Japanese call it kaizen.
So the goal drives the improvement.
Precisely. Key elements include things like a pull production system, where production is only triggered by actual downstream demand. You only make what's needed when it's needed. And Kanban, which is a signaling system, often using cards or containers to control the flow of materials.
So it pulls work through the system.
Right. And the interesting paradox of JIT is that by stripping away inventory, which often hides problems, it actually exposes underlying issues in your system, like machine breakdowns or quality flaws. This forces you to address those root causes, which ultimately improves the entire process.
That's a great insight. So reducing inventory reveals the weaknesses.
And how does quality become total in total quality management, or TQM? That sounds all-encompassing.
It really aims to be. TQM is a systematic approach to ensuring quality across an entire organization. It goes way beyond just, inspecting products at the end of the line.
More than just quality control.
Oh, much more. The emphasis is on involving everyone in the organization, from top management to the shop floor, in activities that provide for continuous, never-ending improvements. The ultimate aim is complete customer satisfaction.
Everyone's responsibility.
Yes. It requires a deep understanding of both the customer and the process itself. And critically, it adopts a prevention philosophy. Instead of just detecting defects after production, TQM focuses on preventing them from happening in the first place.
Prevention over detection.
Exactly. That voice of the customer we talked about earlier is paramount here. It gets deployed throughout the organization using methods like QFD, quality function deployment, to translate customer needs into specific design and process requirements. For companies today, especially in this globalized, liberalized economy, TQM isn't just a nice-to-have competitive advantage anymore. It's often just a qualifier. You need it to even be in the game.
Just table stakes now.
Yeah.
Okay. We've covered a lot of ground on these integrated systems and philosophies. How have the planning systems, in particular, evolved to handle all this global complexity? You mentioned MRP earlier. Where did it go from there?
Right. We've seen a clear evolution there. It really started with Material Requirements Planning, or MRP. Initially, that was just a software program designed primarily to figure out what materials were needed when, basically to avoid unnecessary inventory buildup.
Simple inventory planning.
Relatively simple, yes. This then evolved into MRP-II manufacturing resource planning. This was much broader. Think of systems like IBM's APCS, which stood for Manufacturing Accounting and Production Control System. It integrated something like 19 interrelated modules covering everything from accounts payable and purchasing to shop fleet control and capacity planning. Much more comprehensive.
Okay. Connecting more business function.
Exactly. And the latest iteration, really designed to meet the demands of intense global competition, multi-plant operations, international sites, all that complexity, is ERP, Enterprise Resource Planning Systems.
ERP. We hear that a lot.
You do. ERP systems aim to provide instant access to information across the entire company customer needs, company-wide inventory status, capacity, financials. They often use distributed applications running across multiple layers, handling different languages, currencies. It's a huge leap from simple inventory management to trying to get a truly holistic view of the entire enterprise in real time.
A massive integration effort.
Absolutely massive.
That's a huge leap indeed.
Hmm.
How do these sophisticated ERP systems, or maybe related systems, directly connect with the customer in a more personalized way? Something beyond just tracking orders, you know?
Yeah. That's where we start seeing things like customer-synchronized manufacturing resource planning systems.
Yeah.
These are essentially advanced MRP, ERP-type systems that focus on directly linking customer information with the manufacturing planning and production functions.
Okay, bridging that gap.
Exactly. Historically, customer information, sales data, service requests, preferences was often siloed in different departments like sales or marketing. These newer systems try to integrate that data directly with the main production planning system.
Why is that important?
The goal is really to create customized value for the customer, to deliver more personalized products or services, and even enable companies to anticipate customer needs before they're explicitly stated. This often involves strengthening the entire supply chain, too, by facilitating better partnerships with suppliers based on that customer insight. It's about moving towards proactive fulfillment, not just reacting to orders as they come in.
Oh, anticipating needs.
Yeah.
That's powerful. Okay, one last specific system to touch on. What about when things inevitably get bottlenecked in production? How does optimized production technology, or OPT, specifically address that common problem?
OPT is quite distinct from the systems we've mostly discussed. It's different from push-type systems like MRP or CRP, Capacity Requirements Planning, which plan based on forecasts, and also different from pull-type systems like JIT, which react to demand.
Okay, so what's its focus?
OPT's unique focus is squarely on bottlenecks. These are any resources, whether it's a specific machine, an operation, a skilled worker, whatever, that impede the overall flow of production because they have less capacity than the stages either before or after them.
The weakest link.
Essentially, yes. At a bottleneck, work-in-process inventory tends to build up because products arrive faster than they can be completed. Dr. Eliyahu Goldratt, famous for his theory of constraints, pointed out that the bottleneck effectively determines the overall capacity of the entire production line. Your system can only produce as fast as its slowest point.
Makes sense. So what does OPT do about it?
OPT identifies these critical bottlenecks and then uses proprietary algorithms to schedule everything around them. It focuses on scheduling the workers, machines, and tools at those critical bottleneck points first, ensuring they are always utilized effectively and never starved for work. The non-bottlenecks are scheduled to support the bottleneck. It prioritizes managing the most restrictive parts of the system to maximize overall throughput.
Focus on the constraint.
Got it. So what does this all mean when we try to tie it all together? We've unpacked an incredible array of advanced manufacturing technologies and techniques: CIM, CAD, FMS, JIT, TQM, ERP, OPT. Wow. It seems like the common thread is always about making things better, faster, more responsive.
You're absolutely right. And the crucial point, as our source material really emphasizes, isn't just in acquiring all these fancy technologies. The real challenge and the real opportunity lies in their effective utilization.
How use them.
Exactly. Strategies like CIM and TQM can't just be treated in isolation like checking off boxes. They require appropriate combinations to truly provide suitable manufacturing solutions for a given company's situation. Computerized manufacturing systems fundamentally enhance systemic capabilities, the performance of the whole system, rather than just improving individual point operations here and there.
Right. The whole is greater than the sum of its parts.
Precisely. And the biggest management problems that consistently arise with implementing new manufacturing technologies stem from their profound dependence on integration. There's that word again.
It keeps coming back. Integration not just within the manufacturing process itself, but across the entire enterprise, linking design, engineering, production, marketing, finance, and even extending beyond the enterprise to include suppliers upstream and customers downstream.
So it's about connecting everything.
Everything. This means those critical interfaces like the handover between design and manufacturing, or the coordination between manufacturing strategy and human resource management, training skills, etc., become absolutely paramount. Managing those interfaces well is key.
And that really brings us to a key solution often proposed for these implementation difficulties, the socio-technical systems, or STS approach. Tell us about that.
Exactly. STS analysis provides a framework for designing work systems that achieve truly effective interactions between what we call the social subsystem. That's the people, their skills, relationships, needs.
Okay, the socio part.
Right.
Yeah.
And the technical subsystem, the machines, the tools, the techniques, the knowledge embedded in the processes.
The technical part.
Yep. And crucially, the environmental subsystem, which includes the market, competitors, regulations, and very importantly, the customer.
Connecting people, tech, and the outside world.
Precisely. The STS approach really drives home the idea that the true challenges and successes of implementing new manufacturing technologies are rooted in managing this complex web of integration. It's about seamlessly connecting man, machine, and processes across the entire value chain, always recognizing that the human element is just as critical, if not more so, than the technological one for sustained success.
We've certainly journeyed through the intricate world of manufacturing systems today, from their foundational elements all the way to these cutting-edge integrated systems that really define world-class production now. It's clear that these systems are constantly evolving, aren't they? Always driven by that relentless pursuit of efficiency, quality, and responsiveness to your needs, the customer's needs.
Absolutely. And that relentless pursuit of, never-ending improvements and full integration is what truly defines this space. It never really stops.
Always striving for better.
Always. So maybe a final thought for you, our listener, to ponder. Given this constant drive for innovation, for seamlessly connecting people, machines, and processes, what do you think will be the next truly disruptive force in how products are made? And following from that, what new critical interfaces, those connection points, might emerge as a result of that disruption?
That's a great question to leave us with. What's the next big shift? Thank you for that fascinating deep dive.
My pleasure. Lots to think about.